Uh, right. So in context learning for LLMs is different from few shot learning. So there's another thing called few shot learning in the case of LLMs, in which the LLMs are provided certain particular examples during training time, and then they're also given a few examples during inference time. And then during inference time, the LLMs need to keep on updating their weights again and again. So this is completely different from in context learning. And in context learning is usually faster than few shot learning in this case. Um, So now we can talk about two different types of meta learning algorithms. One is meta learning models. One is in distribution meta learning, and the other one is cross distribution meta learning, um, as can be seen here. So in the in distribution meta learning task, the model tries to adapt itself to new tasks which are similar to the tasks on which it was trained. Whereas in the case of cross-domain meta-learning, the model tries to adapt itself to completely new tasks on which it was not trained at all. So examples of these can be seen uh, in this one. So one example of in-domain meta-learning is, let's say, uh, we want to perform a few-shot image classification using mini ImageNet. There's the ImageNet dataset over here. So in this case, the model would be trained on, let's say, a particular subset of the ImageNet dataset, such as mammals or vehicles. And then the model would have to generalize itself to this dataset. So this is in distribution data set, where the data set on which it is being tested on is really similar to the data set on which it was trained. And in out of distribution tasks, for example, let's say the model is trained on the ImageNet data set, then it'll have to make predictions on, let's say, something completely different, such as the X-ray data set. So those are two examples of meta learning tasks.
What is the difference between continuous?
Huh?
What is the difference between continuous and continuous?
Sorry?
Continuous or lifelong learning. Split the data set into specific sessions, like same as that memo. Like,
oh, so this was just. So is that data set specific?
No, split the data set and learn the whole data set, splitting the sessions.
Mm-hmm.
So like in first session, you only train with mammals, and second session it's trained with like other species maybe. And the goal is to not to forget first session data, to learn continuously learn more things. So the final goal is to memorize all the session data. It seems like similar.
But this doesn't memorize stuff in this case. It tries to generalize itself to other tasks. And in your case, does the task have one big data set and you need to split the data set always, or is this trying to generalize to other tasks?
One big data set, but its final goal is to generalize all data sets.
Okay. So I mean, like it is pretty similar. Like the goal is to generalize to other data sets, but this doesn't work with memorizing stuff in this case.
Is the one thing in this
Oh,
because I noticed if I even just go to the results section, there's meta this, meta that, meta that. There seems to be a lot of purchasing quite a lot of things. Like why would this one?
Sure. So if you look at the paper, they have a certain embedding known as ELMS embedding. So this is what exactly makes this model pretty different from the previous models. And The reason why this is useful is because of something known as causal sequence modeling, in which the sequence in which you provide the input affects the output of the model. But in this case, we do not want it to be a causal sequence modeling. We need it to be a non-causal sequence modeling. So we want there to be a sort of symmetry in so if we provide the input in a particular order, it should not affect the output that we're generating in this case. So there should be a symmetry in that sense. So that's
What is the sequence? Is it batches or
uh,
how do you get the sequence from images in this case?
so we first get the image, and then we so we first getting into an embedding dimension, and then we use the class and we encode the class along with it, and then we combine both of them. That's the input to our transformer model in this case, which is the non-causal.
That's just a single factor. So it's-
Sorry, which one?
when you have the cross transformation, so test it out. If that's just a single factor, so what's the sequence of factors? Or
So we have a bunch of images, query images, and then we have, like, does that answer your question? We have a bunch of query images, and then we convert them into embeddings, and then we concatenate them with the class encodings.
sure.
Okay,
Why do you have this sequence?
sequence of them? Because this is the training data set, right? Because we have this as our data set, and then we have the images on which we want to make the predictions on. I mean, I have a better explanation here. So I mean, so if you look at this, there are n classes, and each of them has k examples of the particular class itself. So that's what we pass in, and then we want to make the model work on a completely different task compared to on which it was trained on. So this is the set of images on which this is the task on which the model will be tested on, basically, if that makes sense.
So it's not a different task, it's just.
I mean, so like, for example, in this case, so like in this, the task could be to say, tell me which breed is this particularly. And okay, you could say in this case, so in this particular case, it's basically the data set that's different, because this could have certain breeds of dogs which this doesn't have, and it could be tested, and the model could be tested on this, on which it was not trained on, basically. But that's just for this example in this case. Yeah. Oh, sure.
So in the trained parameters in the diagram, right, there's like 4 blocks that come out with the sequence model, but there's only one arrow coming to the NLP. What happened to the other 3 blocks?
That's the question. First, look at the terms of CNS, and then the others are the sequence. So one output for every sequence, string sequence to sequence modeling, where we want to consider the sequence.
Sure. I mean, we could just look at the architecture then. So first, okay, so first we'll have a set of query images along with the classes that they're part of. And we would pass them through already a pre-trained encoder, which would convert them to a lower dimension. And for those classes, we'd be using an ELMS class encoder. This is really specific to this paper because the end goal in this case is to preserve symmetry. And that's what this does, because we want for it to be symmetric on the basis of the number that we attach to each label, and also in the order in which we pass the input to the transformer model. So it should be symmetric in both of them.
Like symmetric in the order of the sequence that you feed to your
Yeah,
second. variable.
yeah, yeah.
Why does that happen in your code?
Oh, that's separate from
So if I-
the,
so if I
that's,
just have one added per image. Fine, that's totally different. It's still not gonna break on there, so long as my other one.
yeah, so that was the second thing that we need. The first, so there are two particular symmetric conditions that we need. The first one is, let me see, sorry. So that's the second one you mentioned in the ordering of the input sequence that we pass to the transformer model. But the first symmetric condition that we need is for the classes, so the labels that we assign to the classes. Because I mean, so let's say we have class 1, tiger, 2, dog, and 3, cat. If we permute the 1, 2, 3, we don't want the output to change, right?
Oh, sure.
So that's what they're trying to do in this case.
Okay.
And the way they do it is by using this, in which so in the embedding dimension, all of them have equal angles and all of them have equal magnitude, so that we can't distinguish between them.
So is that like? But isn't that how the limit is like truly zero loss? Like, it only make an ETF when there is truly zero loss.
This is only for the class, like this is just an encoding for the class. So okay, so basically, so we have a class, right? The way we usually do it is we provide a one-hot vector encoding for each class, right? So instead of that, we're doing this. That's all we're doing, if that makes sense. And then we just concatenate the image encoding along with this particular encoding, and we pass it to the transformer model. So yeah, yeah. So I guess we're done with the architecture. I did want to. Oh, there was something else that I wanted to talk about. One second. I mean, I wanted to mainly look at one particular related work because it was really interesting. And it was this paper called Neural Turing Machines, in which they try and extend the traditional neural network by coupling them with some external memory resources, as can be seen over here. So in this case, we have a controller, a memory, read heads, write heads, and external inputs and external outputs. And the controller is pretty much just like a neural network. And the memory is a two-dimensional matrix the memory is a two-dimension matrix in which we need to read and write. And so we'll have how much we need to read and write and where we need to read and write. Those would be dictated by the read heads and the write heads in this. Those would be dictated by the read heads and the write heads. And the controller would just be a regular neural network, which would then receive an input, and it would use these two heads to access the location in the memory and see how much it should write to a memory, and then it would provide us with the output. And then once you keep on training it, it'll work properly. So this was a really cool related work that I wanted to show. And
Is that related to the honor loop architecture?
no, this is something that's similar to meta learning. So there's not exactly that.
In which sense?
Oh, sure. So if I'm not wrong, I think in the memory, it holds the task that it has been trained on previously, and then it tries to work on a new task.
It's memory just like GPS.
Yeah, something like that.
Actually, the pre-training
In this? No, the controller is the neural network, yeah. So the memory is just a 2D matrix in this case. And we'll have the read and write to like read from there and write into the memory matrix. Yeah. Okay.
How can it correspond to this vector architecture?
See?
How can the three model correspond to the H architecture?
So I didn't read in depth about this paper, but like this was referenced in the related work to this paper over here. So this was the paper that I was talking about. Yeah, so the controller is an LSTM or an RNN, could be either one of those. And so this was also something that was related to meta learning, but I'm not exactly sure how it's used for meta learning. We could search it out. So that's another model. That's not this one. Neural Turing machine. Right. It's basically because of the memory that it has that it allows it to work with new tasks. So it can like store and retrieve the relevant information from the memory to perform on new tasks. So that's basically how it works over here. I guess we're nearly done with the paper. So I could just talk about how it's being pre-trained. So in this case, right. So in this case, it's pre-trained on 4 particular data sets. Those data sets are the fungi data set, which is this one, sorry. This is the fungi data set, which is just a plant data set. It is trained on a COCO data set, which is pretty common for object recognition. And it is also trained on a WikiArt data set, which is for art in this case. And we train it on all these particular data sets so that it can generalize itself to other meta learning tasks. And this is the results of this paper, and it performs really well on it performs really well on most of the data sets, but it doesn't perform well on these 3 particular data sets. And they're comparing it with the PMF, which is another meta learning model. And yeah, I think that's it for this paper at least.
This meta learning gets first set from a C data set.
Sorry,
From a C data set, they can use the first set in the same data set.
Forset,
When testing,
right? So when they're testing,
we can use first set in test set.
sorry, Forset?
Support set.
Oh yeah, we use a support set in the, no, I mean, the model doesn't need a support set when we're testing it. We just test it on the data set itself.
So the papers, your contribution is why obviously testing thread, there is the non-casual sequence model.
Yeah, the non-casual sequence model is just like a transformer. It's not anything new.
That is the only one contribution.
Okay, so it has another contribution which is not that great, but so basically there has been no previous benchmark for meta learning tasks. So this basically introduces a new benchmark for meta learning tasks to see how well the models perform on meta learning. So that's what they say in the introduction. Yeah, in this case it's a transformer. It could be anything you want, but in this case it's a transformer. Yeah, I think we're done with this paper. So thank you. Thanks for attending.
Also, like example sponsored by GitHub and you of each student life.